Hello everyone, hope you're doing well today. My name's Ryan Jackson and we're going to be talking about welders today. So Article 630, but more specifically, we're going to talk about the ampacity of the conductors and the overcurrent protection for welders and conductors, because those are the two concepts that people tend to struggle with in Article 630. Article 630 contains requirements like disconnecting means, welding cables, things like that. But the two portions that people seem to really struggle with are the ampacity and the overcurrent protection. So that's what we're going to be focusing on in this video. This will be based on the 2020 version of the NEC, although these rules haven't changed for quite some time. So 630.1, I almost always like to start with the scope of the article before I start jumping into the rules, because a lot of times something in the scope can be kind of surprising, and we want to make sure that we have as much information as possible before we start applying the code rules. So 630.1, the scope, says this article covers arc welders, resistance welders, plasma cutters, and similar welding or cutting equipment. So if you didn't read the scope, you might not know that a plasma cutter is considered a welder as far as the NEC is concerned. More specifically, it's an arc welder. So if we're doing a plasma cutter, then we would want to follow the arc welder requirements. So we have arc welders and resistance welders here in Article 630. Arc welders, 630.11 addresses the ampacity of conductors for welders. And I guess really before I dig too deep into this, we ought to explain the difference between an arc welder and a resistance welder. I'm not into welding. It's not something that I've ever really cared too much about. One of my hobbies is working with wood, and you might be able to see some of the bases and things that I've turned on the lathe. But welding has never really interested me. So if I say something incorrect about the difference between arc welding and resistance welding, I'm sure somebody will leave me a comment on YouTube and let me know. But my understanding of arc welding is that it has an electrode, like a welding rod or wire. We have the two items, and then we have a third item, an electrode, that we melt and join the two materials together. Whereas with resistance welding, we don't have that third item. We just have the two items that we're going to weld together. We heat them up and we weld them together. So that's kind of the difference between arc welding and resistance welding. 630.11 addresses the ampacity of conductors for one arc welder. 630.11b addresses the ampacity of conductors for more than one arc welder. And then 630.12a addresses the overcurrent protection for the welder, and 630.12b addresses overcurrent protection for the conductors. So we have to be careful when we read these rules. 630.11 is easy enough. It's the wire size, and it depends on whether you have one welder or more than one welder. 630.12 provides the overcurrent protection. Now, for most equipment in the code, we have different rules for protecting the equipment and the conductors. If I'm doing a transformer, for example, I read Article 450, Section 450.3, to learn about protecting the transformer itself. For protecting the conductors, I would go to Article 240. Just like a water heater, it's an appliance, I would read Article 422 to protect the water heater. I would read Article 240 to protect the conductors. Now, here in Article 630, there's not quite as much jumping around, but we do have specific rules for the equipment and different rules for the conductor, and we need to make sure that we satisfy both requirements for overcurrent protection. So let's start out with the conductor sizing. 630.11a, conductors for one welder. The ampacity of a conductor that's supplying just a single arc welder must not be less than the I1F value on the nameplate. Okay, so let's take a dive through the nameplate here. I don't see any I1F value. So let's keep reading. It says, if no such value is specified, then the primary current of the welder is multiplied by the factor in Table 630.11a based on the duty cycle of the nameplate. Now, I know that it's kind of small up here in the top left, but if I go to 630.11a, and hopefully you've got a code book, you're following along, you would look at the duty cycle. This is a non-motor generator arc welder. So I would be down here, the duty cycle is 30% as marked, and it says 0.55 is the demand factor. So we're going to take our 78 amps, which is our primary current, multiplied by the demand factor of 0.55. So once we do the math, 78 amps times 0.55, that equals 43 amps. So we need a 43 amp conductor. If you're familiar with conductor sizing, you might remember back in Article 110, back in section 110.14, C1, it says if you have equipment rated 100 amps or less, then you have to use the 60-degree column when you're sizing conductors. And if it's greater than 100 amps, we would use the 75-degree column, unless the equipment actually specifies a different rating. So if our equipment does not give us any specific ratings as to the temperature ratings, we would use the 60-degree column, and we need to find a 43 amp wire. So we would use 6 gauge at the 60-degree column. If our welder and the receptacle or circuit breaker, whatever it's connected to, if each end of my conductors actually had equipment rated 75 degrees, then I could go ahead and use an 8 gauge conductor. So we're going to take either the I1F value, or we're going to take the primary current times the duty cycle multiplier in 630.11a. So we're either going to use 6 gauge or 8 gauge, depending on the ratings of the terminals. If I have more than one welder, things get a little bit more convoluted. For conductors supplying more than one welder, the duty cycle demand factors that we just talked about in A are applied to each individual welder. And then the current of the two largest welders are added together at 100%, plus 85% of the third largest, plus 70% of the fourth, plus 60% of all of the remaining welders. All right, so if I had welders of different ratings, I would do the duty cycle demand factor first, and then I would determine, I would put them in a list from largest to smallest and apply the demand factors that way. In the example we're going to do, we're just going to say we have 6 welders that are all the same rating, because a lot of times that's going to be what we have. So here we have 6 welders of the one that we just looked at. We went through and we did the demand factor at the 30% duty cycle, and we found out that it's a 43 amp demand factor. So we've got a 43 amp welder for all intents and purposes. That is our first 2 welders, right? Because the first 2 are taken at 100% of the demand factor. So that's 2 of them at 43. And then the next one, we're going to take our 43 demand factor times it by 0.85, and we're going to call that welder a 36.55 amp welder. And then the next one at 70%. And then the last 2 at 60%, which is 25.8. So if we add all those together, 2 of them at 43, 1 of them at 36.55, 1 at 30.1, 1 at 25, and 2 at 25.8, that means the conductors have to be rated at least 204 amps. And if I go back to table 310.16, we'd find out that that's either a 4-aught copper or 250 kc mil aluminum. So those are my conductors for more than one welder. So if I just have one, then we're either going to use 6 gauge or 8 gauge. If we have more than one, we're going to go ahead and use 4-aught copper or 250 aluminum. So that's the conductor size. When it comes to the overcurrent protection, 630.12 says that the overcurrent protection for the welder and the conductors is required. And if the rating of the overcurrent device does not match a standard rating indicated in table 240.6a, the next higher standard size can be used. Now, 630.32 for resistance welders is going to say the same thing. It's going to say, look, when you do the math, if the math doesn't correspond with the standard rating of a breaker or fuse, go ahead and use the next standard size up. So in case I forget to mention that in 32, it's the same concept for both arc and resistance welders. Let's do an example. 630.12a is overcurrent protection for the welder. Has nothing to do with the conductors. This is just to make sure that the welder is protected. Welders have to have overcurrent protection rated not more than 200% of the I1 max value on the nameplate. All right, well, again, we're unlucky. Our nameplate does not have an I1 max value. If we did, it would be nice and simple. We'd take 200%. So we keep reading. If that value is not indicated on the nameplate, then the overcurrent protection must not be set higher than 200% of the primary current rating. All right, so again, we're going to be operating this welder at 208, and it is a 75 amp welder. So we're going to multiply that by 200% plus if we wanted to, the next size up. 78 amps times 2 is 156 amps. Of course, 156 amps is not a standard rating of breaker or fuse. I would go to table 240.6a to find that material. Can't go to the store and get a 156 amp breaker. So what are we going to do? Could we put it on a 150 amp breaker or fuse? Sure. Yeah, we could if we wanted to. Could we put it on a 175 amp? Sure. But that would be the limit. Putting it on a 200 amp breaker or fuse would be a violation, right? So the maximum is 200% plus the next size up if that doesn't correspond. So 175 amp maximum. That protects the welder. So we're going to write that number down. Under no circumstance can we exceed 175 amps. We write that on a piece of paper and we push that off to the side. And then we do a different calculation to protect the conductors. And then we need to bear in mind that both have to be satisfied. Conductors supplying welders must have overcurrent protection set not higher than 200% of the conductor's ampacity. All right. When we figured out the ampacity, we figured out that we're going to use a conductor that's basically rated 50 amps. So right off the bat, we know if we pull a 50 amp wire, we got a maximum fuse or breaker of 100 amps, because to protect the conductors, I can't use greater than 200% of the ampacity. Well, if I used a 100 amp breaker for my welder, that would protect the welder and it would protect the conductors. But here's the problem. When I go to turn the welder on for the first couple of seconds, it might not hold. It might trip the 100 amp breaker. So now I need to start kind of changing some things around. I need to make sure that my welder can actually work. You know, it's one thing to have it safe. It's another thing to have it functional. So we're going to increase the size of the rating or of the breaker to ensure that it will actually hold. And as we know, we could go up to 175 amps. So let's say that we decide to go to a 150 amp breaker. 150 amp breaker, we know will protect the welder, but it would not protect those 6-gauge conductors. So I would have to increase the size of the wire so that they're protected. So if I decided to use a 150 amp breaker, then I would divide that by 2 to get my minimum ampacity of conductors, and that would be a 4-gauge conductor. Or if I wanted to use a 175 amp circuit breaker or fuse, then I would take 175 amps and divide that by 2, which would leave me needing an 88 amp conductor, which would be 3-gauge. So we need to remember that we have to protect the conductors and we have to protect the welder. And sizing the wire for the welder is going to result in a pretty small conductor, oftentimes that is not protected by the overcurrent device. So usually we'll have to use a larger conductor than what the welder would require simply to protect the conductor from overcurrent. So that's an arc welder. Let's take a peek at resistance welders in 630.31 and 630.32. So for resistance welders, same concept. 31A addresses the ampacity of conductors for a single welder. 31B addresses the ampacity of conductors for more than one. And then, of course, 32A is overcurrent protection for the welder. 32B is overcurrent protection for the conductors. All right, so item 1, when it comes to ampacity, is kind of strange, but remember with resistance welders, a lot of times this could be as part of like an automated process. So robotics, where the welding is automatic and automatically fed and the operation is all automated. And it could be doing all sorts of different things throughout the day. So when we read item 1, it says for resistance welders, the ampacity of the supply conductors that can be operated at different values of primary current or duty cycle must not be less than 75% of the rated primary current for seam or automatically fed welders, and 50% of the rated primary current for manually operated non-automatic welders. So it depends on whether this thing is an automated procedure and whether or not it's used at different duty factors. Let's go ahead and do an example. If I have a resistance welder that's fed automatically, but is used at differing duty cycles, the rated primary current on the nameplate is 174 amps. All right, so 174 amps times the 0.5 demand factor is 87 amps. So I would need a conductor that can carry 87 amps. That would be a 2-gauge copper conductor if the terminals are only rated 60 degrees, and it would be a 3-gauge copper if they're rated 75 degrees. All right, so we're going to size our conductors based on how the welder is operated. Item 2 is nice and simple. If the duty cycle is constant, then the ampacity of the conductor supplying it must not be less than the primary current rating multiplied by the duty cycle demand factor in table 630.31A2. So it's very simple, or pardon me, very similar to how we do an arc welder. So here on our nameplate, it says 174 amps, 50% duty cycle. If I go to table 630.31A, it says that the demand factor is 0.71 for a 50% duty cycle. So I'm going to take my 174 amp nameplate, multiply it by the 0.71 demand factor, and that leaves me with a requirement of 124 amps for the conductor. So I need a conductor that can carry 124 amps. I would use the 75-degree column, and that would be 1-gauge copper, which is rated 130 amps. So sizing one welder that is used at a constant duty cycle is a pretty simple approach, really. Take the nameplate, take the duty cycle, use the demand factor, do the math, and stab in whatever 310.16 tells you to use. If I'm using more than one resistance welder, I've got a group of welders, well, the ampacity of conductors supplying more than one resistance welder must not be less than the largest welder plus 60% of all others. So it's not quite as convoluted as a group of arc welders where we had, the first two at 100% and then the next one at 80 and then 70 and then 60 and da-da-da. This one just says, look, take the biggest one at 100% of the demand factor and then all of the rest at 60%. So if I have two of those welders that we just looked at, 174 amp primary current, 50% duty cycle, I would take my 174 times 0.71, and that's my 124 amps. So that is the demand factor, the demand load for the one welder, and I'm going to take that value at 60% and add the two together. So 124 amps plus 74 amps is 198. I would need a 3/0 copper conductor, which is rated 200 amps, or I could use 250 Kc mil aluminum, which is rated 205. Sounds like my neighbor's dogs are saying hello. When it comes to the overcurrent protection, it's actually really simple for resistance welders, much easier than for arc welders. Resistance welders must be protected by an overcurrent device that's rated not more than 300% of its primary current rating. Nice and simple. So, primary current rating on this one was 174 amps. I'm going to multiply that by 3, which is 522. I go to table 240.6a, and I come to realize that 522 amps is not a standard rating of fuse or breaker. So I go to the next size up, which is 600. Now, could I use a 500 amp breaker? Sure, I certainly could, but I could also use a 600 amp as well. When it comes to protecting the conductors must be protected by an overcurrent device rated not more than 300% of their ampacity. All right, so it's the same requirement for the welder and for the conductors. Now, we decided earlier that we were going to use 1-gauge copper for one of these welders because that gives us 130 amps of ampacity and we only needed 124. So 3 times my 130 amp ampacity would allow for a 400 amp overcurrent device. I could use a 400 amp breaker. That would protect the welder and it would protect the conductors and we can go home. But if I needed it to be rated higher than that because we need the welder to actually work, well, I might use a 600 amp circuit breaker for the welder. That would be the maximum. I would take my 600 amps, divide that by 3, and that would be the minimum size conductor that would be protected by the overcurrent device. So I would need a 200 amp wire in order to be protected by a 600 amp overcurrent device. Of course, if I wanted to use a 500 amp overcurrent device, I would take my 500 amps, divide that by 3, and find my conductor that way. So there you go. arc welders and resistance welders, ampacity of conductors, overcurrent protection for the welders, overcurrent protection for the conductors. Hope you enjoyed the video. If you'd like me to cover anything specific, please reach out to me and I'll do the best that I can. Thanks everybody, and I hope you have a great day.
Be sure to like, follow, subscribe, and ring the bell.